Hi everyone and welcome back to Physics 2B. Today we are going to start talking about electric potential and electric field. Okay, so let's go ahead and get started with the idea of potential energy. So in the electrical case, in electricity, we see that it's very similar to the potential energy due to gravity. So I have this picture here from the textbook, and as we remember from Physics 2A last semester, the potential energy due to gravity is equal to the negative change in kinetic energy. Okay, so this idea that our kinetic energy and potential energy is very related to each other in this sense it's very similar to the kinetic energy and potential energy due to an electric field. Okay, so these two here are very similar. So a charge that is accelerated by an electric field, so this is our E field here, shown by these lines. Field. It is accelerating this charge Q, and that is very similar to our mass here being rolling down this hill. Okay, in both cases we have potential energy that is being converted into kinetic energy. Okay, and remember from last semester or when you took Physics 2A, that work is done by a force that is conservative. Okay, so W, or the work, is equal to the negative change in potential energy. Okay, so work done to accelerate a positive charge from rest is positive and results from a loss in potential energy, or it gives us a negative potential energy. Okay, just like so. So again, work done to accelerate this positive charge from rest is positive, and results from a loss in potential energy here. Okay, so let's go ahead and start talking about electric potential. And this is noted as capital V. We typically in this course, we might just call it potential. Okay, and we define this electric potential, as the potential energy per unit charge. Okay, so we have that here. Electric potential is the the electric potential is equal to the potential energy divided by the charge that we have. Okay. We also define something that's called potential difference, and that is noted as delta V here. And it quite literally is the difference between 2 points. Okay, so it's the difference between the electric potential. So difference, let me try to think. Potential difference between 2 points A and B can be described as this here. So this are our electric potential, and this would be at point B. Okay, and then this would be the electric potential at point A. And it is still related to the potential energy divided by Q, but now it is the difference in potential energy. Okay, and this is going to provide units or give us units in joules per coulomb, because remember that Q is in coulombs, or C, and potential energy is in joules, or J. Okay, So this defines, or it has been defined, that joules per coulomb is equal to volts. Okay, so this is a volt. Okay, and when we talk about potential difference, the common name for this is voltage. So when you look at a battery, it'll give you some sort of voltage, or a wire. This is what we're talking about, is potential difference. Okay. All right, so now let's talk about potential difference and electrical potential energy. So we have this relationship here that we looked at earlier, and we can um, switch this around to be the change in potential energy is equal to Q, or our charge, times our change in V. Okay. Remember that voltage is energy per unit charge. Okay. So this is just a restatement of what we just looked at. Okay. So let's go ahead and use this now in an example. So this is example 19.1. Whoops. And it states, suppose you have a 12-volt motorcycle battery. Okay. 12-volt motorcycle battery. And that can move 5,000 C, or coulombs, of charge, and a 12-volt car battery that can move 60,000 coulombs of charge. How much energy does each deliver? So we are looking for energy, or our potential energy. So remember that V is equal to our potential energy divided by Q. Okay. And we're looking for how much energy. So let's go ahead and rearrange that to potential energy is equal to Q times V. Let me just quickly make a note. Another student pointed this out to me. I write my Q's this way. Okay. Typically Q's are written this way, or maybe this way, something like that. This is just something that I do. So bear with me with that. Okay. So when you see something like this, it is going to be a Q. Okay. All right. Q for charge. Okay. So let's look at this first case. So we're going to look at the motorcycle. So I spelled that wrong. Oh man. Give me just a second. Motorcycle. I know this isn't super important, but it's going to bother me. Okay. For the motorcycle, we can calculate the potential energy. That is going to be Q, or our charge, which is 5,000 coulombs, times our voltage, which we know is 12 volts. Okay. And then we can get our calculators out. So 12 times 5,000 is going to be 60,000, and that is going to be in joules. Okay, so this is the amount of energy that our motorcycle can deliver. Okay, now what about our car? Car has potential energy equal to our charge, which is 60,000 coulombs, and same voltage, so 12.0 volts. So let's take 60,000 times 12, and we get 72,000. No, forgot a zero. Eraser. 720,000 joules. Okay, so we can see that difference here. We've got at least 10 times as much, right? All right, so this is the amount of energy that each battery can deliver. All right, let's look at one more example. It states when a 12-volt car battery runs a single 30-watt headlight, how many electrons pass through it each second. Okay, so with this one, it's going to take a little bit more thinking. So we have our voltage, V, right? We have watts. Do you guys remember watts? Maybe. So a watt is joules per second. Okay, so now we can find our energy. So we have our power, I believe. We have our power, 30 watts or joules per second. And we want to know how many electrons pass through it each second. So we can find our, let's quickly think about our potential energy equation. So potential energy is equal to charge times our voltage, our potential difference, and our potential, sorry. And we have this guy. We don't have our potential energy each second, but it looks like we want a rate anyway. We need to know the charge of an electron. So let me quickly find that in our textbook. Bear with me for just a moment here. Let me see here. Okay. So Q for an electron is negative 1.6 times 10 to the negative 19th coulombs. Okay. Okay. So this is power. I don't want to get confused here. So we know that we're looking at every second. So we can set that aside for a minute. And we can say that our potential energy is 30 joules, and this is every second. That's our potential energy. So, excuse me. We want to look at this, but we want to also look at the change. So we want to look at the change in potential energy. Oh, I see what I did. Messed up here. Okay, so this is the charge, but this is a charge for one electron. Okay, we want to know the charge that's going on in this battery, okay, or how much charge it can move. Just like the last problem that we did, here it told us that the car battery can move 60,000 coulombs of charge. So that's what we're looking for right here. Okay, so first we need to find out how many coulombs of charge can the battery move. Then from there, we can find out the number of electrons that are moved each second. Moved, I'm just going to say that. Okay. So we are looking for Q here. So we've got our change in potential energy, or our potential difference, or potential energy, sorry, is equal to Q delta V. Okay. And so we want to solve for Q. That equals change in potential energy over the change in V, or voltage. Okay. Note that, let's see, is it our potential energy will our potential energy is being produced and used every second. So we're going to have a negative potential energy. Okay, so this should be negative since we are losing energy. Okay, so we are losing energy to the headlight, so we need to account for that by putting in a negative here. Okay, so Q should be negative 30 joules divided by delta V, which is 12 volts. So we should get a value of 30 divided by 12 is 2.5. Okay, and this is in coulombs. So this now is the amount of charge that the battery can move. Okay, so amount of charge. The battery can move. Okay, so that's what we have here. Now we want to find out how many electrons that is. Okay, so this is per second. I should say per second. Just make note of that. We still have that in our brain. Okay. All right, so for each electron, we have this charge here. So we've got negative 2.5 coulombs. That's what we have here. That's our charge. And we're going to divide it by 1.60 times 10 to the negative 19th coulombs, and that is per electron. Okay. So we have our charge overall. Then we have this, we can say that this is a conversion, right? Because we have amount of coulombs per electron. So we'll take 2.5 and divide it by 1.6 times 10 to the negative 19th. So we get approximately 1.56 times 10 to the 19th. Oops, that should just be a 0. 10 to the 19th. And this is now electrons. Okay, so this is the number of electrons that pass through the battery each second. Okay, so this is what we have. This is the number of electrons that pass through that battery each second. Okay. All right, I know that was kind of all over the place a lot, but if you have questions about it, please ask me, and we can go over it again in class, okay? All right, this is where I'm going to pause, and then we will continue in the next video talking about, let's see what we're going to talk about, starting with electron volts.